The Department of Materials Science and Engineering at UCI is home to impactful research enabled by impressive facilities and equipment for every step of the research process. This video will highlight some of the unique and cutting-edge facilities and research capabilities found at UCI. In this video, we will spotlight some of the equipment used in Professor Julie Schoenung's labs. Her group conducts research on novel materials and manufacturing techniques and focuses on powder metallurgy and ceramics. You will also get to see some of the impressive shared facilities available to all graduate students in the department. Daryl Mack, our department's research and development engineer, will start us off by introducing the Schoenung Lab's powder production capabilities.
Let's take a quick look at our spray atomization facility in Engineering Gateway. The first set of pictures we see has a basic overview of the system, along with a detailed shot of the powders. Our newest version, although it looks much more complex, essentially does the same thing. The top part of the system is the melt chamber. Inside of that is a coil that's being fed by a 50 kilowatt power supply that surrounds a crucible where we put the metals in that we're interested in melting. At the bottom of the crucible, there's a nozzle. Once we've hit the right temperature, we allow the metal to flow through the nozzle. From there, the molten metal passes through a gas jet, usually argon or nitrogen. The gas jet turns the column of metal into fine droplets, which then solidify into a powder. From there, they continue down the entire length of the chamber, entering a cyclone separator where the particles lose energy and settle to the bottom of a capture pot. This video shows an actual atomization run of aluminum around 850 degrees centigrade. This atomized powder can then be used in research projects, studying mechanical alloying, additive manufacturing, and more.
To achieve nanostructured powder and eventually nanostructured bulk material, gas atomized powders can undergo mechanical alloying to refine their grain sizes. One of the Schoenung Group's research focuses is on fabricating nanostructured materials for their unique properties such as high mechanical strength. The cryomill shown here is useful because it can be used to achieve nanoscale microstructures in atomized powders. Bulk nanostructured materials can be achieved by consolidating mechanically alloyed powder, which is made when powder is mixed with a milling media, in this case ball bearings, which induce severe plastic deformation in the powder. The severe plastic deformation causes grain refinement in the mechanically alloyed powders, down to the nanometer scale. Initial powder microstructures such as nanometer grain sizes and solid solutions produced during mechanical alloying can be retained using non-equilibrium consolidation processes such as spark plasma sintering. Spark plasma sintering, or SPS, works by applying a high uniaxial load and a pulsed DC current to rapidly heat and consolidate powder into a bulk material. The rapid heating in SPS prevents grain growth and equilibrium structures to form in consolidated materials while still fully densifying the sample. The SPS is one of the most used pieces of equipment in the Schoenung Group and is used to produce nanocrystalline alloys and ceramics for a variety of applications and projects. Gas atomized powders that don't undergo mechanical alloying have a spherical shape, which makes them ideal for additive manufacturing. Additive manufacturing is a technique where parts are built layer by layer, and it has many benefits over conventional manufacturing, such as the ability to create complex parts with minimal waste. Another research focus in the Schoenung Group is on an additive manufacturing technique called laser-engineered net shaping, which Katie will explain next.
This Optimec laser-engineered net shaping system is used to 3D print metals and ceramics. During this technique, powders are directed towards the focal point of a high-power laser to create a molten pool of material. The stage is rastered back and forth according to the computer-aided design model, with material added layer by layer until the full 3D part is built.
Outside of Professor Schoenung's group, there are plenty of additive manufacturing capabilities available to graduate students. UCI's Institute for Design and Manufacturing Innovation, also called IDMI, is an institute for advanced manufacturing techniques that integrates research, education, and community outreach. IDMI is directed by Professor Lorenzo Valdivit, who has more than 15 years of experience in designing, modeling, manufacturing, and characterizing architected materials and multifunctional structures. IDMI hosts world-class facilities with the latest additive manufacturing technologies and design and modeling capabilities. Students can 3D print biomaterials, metallic components, and structural polymers. At IDMI, students can 3D print metallic structures through selective laser melting. This SLM uses a laser to selectively melt layers of powdered metallic materials to create complex components. In addition to the SLM, IDMI has capabilities for other additive manufacturing techniques like material extrusion, material deposition, and vat polymerization, among other things. Laser cutters, 3D scanners, and subtractive equipment are also available for use. Whether you use powder consolidation, additive manufacturing, or any other material fabrication technique, you will have access to world-class characterization facilities through the Irvine Materials Research Institute, also known as IMRI. This interdisciplinary research program operates as a hub for materials research across UCI's campus, as well as for guests from outside of the university, including industry and nonprofit organizations. IMRI is directed by Professor Xiaoxing Pan, a world-renowned materials scientist and electron microscopy expert. IMRI provides advanced equipment and techniques that can be used for structural and chemical characterization, advanced imaging and spectroscopy, surface analysis, and much more. Graduate students can be trained on any equipment by IMRI's expert scientific staff. The next few segments will highlight a few of the facilities available through IMRI. We will begin with the Temper Lab, which is home to a variety of state-of-the-art characterization instruments capable of measuring materials' thermal, elemental, mechanical, physical, and rheological properties. Temper was established in mid-2019 and is the newest IMRI facility. The equipment available in Temper is useful for the physical property characterization and elemental analysis of bulk and thin film biological, soft, and hard materials. Shown here is the NECH F3 Jupiter, which has simultaneous capabilities for both thermogravimetry and differential scanning calorimetry between 25 degrees Celsius and 1600 degrees Celsius. This high-throughput machine provides measurements that give information about phase transformations, which is useful for designing new materials and microstructures. Graduate students can also take a close look at the microstructures and phase composition of their samples at the Laboratory for Electron and X-ray Instrumentation, or LEXI. The facility includes 2 scanning electron microscopes that can be used for cross-sectional imaging, electron backscattered imaging and diffraction, compositional analysis, and much more. Shown here is the FEI Magellan, which is an extremely high-resolution scanning electron microscope. This SEM enables sub-nanometer resolution and high surface sensitivity and is capable of light element analysis, fast elemental mapping, and electron beam lithography. In addition to its microscopy capabilities, LEXI is equipped with 2 X-ray diffractometers. Here you can see the Rigaku Smart Lab, which has measurement packages available for powder and thin films, high-resolution X-ray reflectivity, small-angle X-ray scattering, and microdiffraction. Next, Katie will introduce LEXI's X-ray photoelectron spectroscopy instrument.
The Axis Super is part of the LEXI Lab facility. This is a surface science technique called X-ray photoelectron spectroscopy. The LEXI Axis Supra has many more capabilities than just XPS. For instance, air-sensitive samples can be loaded into the main chamber using this glove box. Additionally, there's a surface science station on the side of the instrument where samples can be heated and analyzed at the same time. There are also additional analysis techniques such as ultraviolet photoelectron spectroscopy, Auger electron spectroscopy, and scanning electron and Auger electron microscopy.
For even finer imaging down to the nanoscale, researchers can go to the Center for Transmission Electron Microscopy, or CTEM, which houses 4 TEMs and a full set of TEM specimen preparation equipment. The GL2100F TEM is equipped for imaging of material and biological specimens at cryogenic temperatures. Its control system is simple and intuitive to use, and users can operate it in bright field and dark field modes for a wide range of applications. The GEOL-GEM 2800 TEM can be used for high-resolution imaging and transmission or in scanning transmission electron microscopy. Some popular applications for this microscope include rapid elemental mapping, in situ experimentation, and strain and orientation mapping. The GEOL Grand Arm offers sub-angstrom spatial resolution for atom-by-atom chemical analysis and atomic resolution STEM imaging of various materials, among other things. The Grand Arm is ideal for a variety of in-situ experiments to learn about the structure, properties, and dynamic behavior of nanostructured materials under applied fields, stress, and reactive environments. The facilities we have shown you are just a taste of what is available to graduate student researchers in the MSE department at UCI. The top-class research capabilities and engaged faculty present exciting opportunities for internal and external collaboration. The recently established NSF MRSEC at UCI, the Center for Complex and Active Materials, is an interdisciplinary research center that focuses on advancing foundational knowledge towards the development of complex concentrated materials and active biomaterials that may offer unique functionalities and superb performance. This center fosters collaboration within the department and with other institutions and is made possible by UCI's dedication to multidisciplinary research, experiential learning, and diversity. Formally established only 2 years ago, the MSE department at UCI is still young and continues to grow and attract new talent, building upon its top-notch faculty and facilities. We hope this small taste of the research facilities and capabilities available in the MSE department at UCI encourages you to join us. For more information about the department, IDMI and IMRI, and the Center for Complex and Active Materials, please visit the web pages shown here.